All right, this is the 2.1 notes, the video that I have. So for this video here, we've got 2.1 limits, rates of change, secant and tangent lines. Now, normally for these videos, and for my lecture notes for that matter, I don't usually have, or rarely do I have, a big page of text. Some sections might be denser with text than others. Usually it's mostly definitions and theorems and lemmas and content of that nature. Rarely do I have just a big wall of text and me just talking to you. At the beginning of calculus, I feel it's very important to develop a deeper intuitive understanding and to adopt a perspective of exploration and curiosity, because these are the sorts of motivations that led to the development of calculus, sort of answering these questions. So that's not usually going to be how my notes go, but for this first section, please do not be intimidated. There is a lot of text in this first page. I would urge you just to read it. You can pause the video, you can look on D2L. But the idea here is that rates of change. So in particular here, let's talk about how our position changes. So the rate of change of position with respect to time. So how does someone's position change based on the amount of change in time? That's what velocity is. Velocity is the rate of change of position with respect to time. So this first page is really trying to communicate that you can estimate how fast you are traveling at a single moment in time, what your instantaneous velocity is. So, in other words, what your speedometer would read, or if you were traveling on the highway and a cop tagged you with a radar gun or something, that would report back your speed in that precise moment in time. We can estimate that based on your average velocity. Average velocities are much easier to calculate. For instance, if you travel 120 miles and it takes you 2 hours to do so, on average you are traveling 60 miles an hour. But we know that that doesn't mean that you were traveling 60 miles per hour the entire 2 hours, because at the very least we know that you didn't just appear in a car traveling 60 miles an hour. You started from a car that was in park, that was traveling 0 miles per hour. You then had to go from 0 to 60 at some point. And you probably went not directly 0 to 60, but you went up and down. You went to 25, you slowed back down to a stop at a stop sign. So your velocity is changing all over the map. So we can still use your average to calculate, to estimate your instantaneous rate of change, your instantaneous velocity. If we know, if we have information about about your distance on a really short time scale, for instance, maybe seconds, maybe if we know that you were at mile marker 330 at one time, and then 6 seconds later you were a tenth of a mile away, we could use that to figure out and roughly estimate that you're traveling 60 miles per hour. And since it was only a 6 second interval, it's unlikely that your speed changed that much in 6 seconds. All right. Really what we're going to do today is take a look at example 1, but I've developed a nice little web app on Desmos. I've created a nice little calculator, a graphing utility for you to play around in. So let's go ahead and read example 1, and then let's migrate over to Desmos. So example 1, a hammer falls off a scaffolding at t = 0 seconds. Let's estimate the instantaneous velocity of the hammer at 0.8 seconds. If the hammer's position t seconds after beginning to fall is modeled by this function s of t = 4.9 t squared. So this function s of t, you plug in how many seconds after it was dropped, or fell, began to fall, And then you just plug in that t value and it will report back how much distance it has since traveled in that amount of time. So if we go ahead and take a look here at Desmos, let's go ahead and migrate there. All right, so now that we're here in Desmos, we've got that example one from the 2.1 notes graphed. So right here, this red piece of a parabola is exactly s of t equals 4.9t squared. I have a lot of the graphs and stuff kind of hidden away in these folders because this is there's a lot going on that what meets the eye. But you can see it's right here. This video is not intended to be a Desmos tutorial. There's plenty of those online already, and Desmos' help page for like their quick start guide is very useful. But I have all the actual stuff under the hood hidden away in these folders. So here is the hammer graph. I'm only graphing it on this 1 second interval because the question asks us about the time 0.8 seconds. So we certainly don't need to graph much more than what I have graphed. So let's go ahead and calculate the average velocity for this. Okay, so this is this Desmos exploration that I'm doing right here is a bit more involved than what example 1 asks us. We'll get an answer to example 1, but this is sort of more of a holistic approach. So there is a little bit more in here than the bare minimum needed to answer example 1. We've got a little bit more of an introduction. So let's go ahead and calculate the average velocity. So if we know the moment of release happens at t equals 0 seconds, and its current position, in other words, or the amount it has since traveled is 0 because it hasn't yet fallen, it's just been released. 1 second later, we're here at 4.9 meters. So the total distance traveled in this 1 second interval is 4.9 meters. Well, if the distance traveled is 4.9 meters and the time it took to travel that is 1 second, then we just divide them. So 4.9 divided by 1 is 4.9 meters per second. And that's exactly what's going on right here. We do final position minus initial position, so 4.9 minus 0, and then divided by the change in time, 1 minus 0. Note that we really just did rise over run from this point 0, 0 to this point 1, comma 4.9. And this is exactly just your regular old slope formula. Another question here is, does this mean that the hammer has been traveling 4.9 meters per second the entire 1 second duration that's graphed here? Absolutely not. We know that the hammer was on the scaffolding, so it had a velocity of 0 at that moment, and then it began falling. Someone knocked it off or dropped it. Whatever the case may be, before it began to fall, it had a velocity of 0. And then because we know how gravity works, we're all familiar with dropping things, hopefully. When you drop something, especially something that is not very easily affected by air resistance at low velocities, like a hammer, unlike a feather or something, but a hammer, when you drop it, it begins off at 0 velocity, and then its speed just increases. The longer it falls, the faster it gets. And this model that example 1 has, it's not taking into account air resistance. This 4.9 t squared is not accounting for any frictional forces due to fluid motion. So this hammer, according to this function, would just fall forever and become as fast as it wants to. The longer it falls, the faster it becomes. So definitely the velocity is increasing. The velocity is increasing. Okay, let's go ahead and talk more about this slope formula here. So the average velocity here was just the slope formula for the line connecting these 2 points, 1 comma 4.9 and 0 comma 0. So 4.9 right here, that's the slope of this blue line. Let's go ahead and draw that. And when we draw that, that's called a secant line. Whenever you take 2 points of a graph and you connect them with a straight line, that line's called the secant line through those 2 points. And the slope of that line, the slope of the secant line, is the average rate of change of that function. Not of the line, but of the curve, of the function, of the graph where you selected the 2 points. Okay, so the secant line shows that this would be the position function of an object that traveled at a constant 4.9 meters per second. And as you can see that the red function, its curvature is very different than that of the straight secant line. This means that the hammer's velocity is certainly changing because the curvature, the slope of that red graph changes as you move from the bottom, 0, 0, to the top, 1 comma 4.9. Okay. Let's take a look at this instantaneous rate of change. So here's a question. Is there a moment during the hammer's descent where it was traveling at 4.9 meters per second? We know the average was 4.9 meters per second. But does that mean at any time on the hammer's descent was it actually traveling that average? Or you can think of it in a different context. Let's say you get into a car and you travel for 2 hours and you travel 120 miles. Does that mean at some point on your journey your speedometer read 60 miles per hour? All right, so another way we could think about this is we can restate it in a geometric way. So this is the last little thing down here, equivalently, is there a point on the red graph where the little line segment that I have drawn here, I've only drawn that to give you a sense of what the slope is really close to this point, right? We could like zoom in here and you see how the curve is like indistinguishable from the purple line here. It's only when you deviate sufficiently far away that they begin to separate. So that purple line there, it has a special name in calculus, but for right now, you should just think of it as like a guide to get a sense of what the slope looks like. Okay? So can we find a point on the red curve where the slope of this purple line, this guide line that I have drawn, that line's slope is parallel? In other words, it's equal to the slope of the blue line. Quantitatively, that means that they're equal, the slopes. So that means when is there a point on this purple line, where on the find a point on the graph of the red function where the slope is 4.9, the instantaneous slope. The curvature is 4.9. So what we can do here is we can use a slider below, this H slider. Oops, sorry, wrong slider. The C slider, I meant to say. We can use this slider. So up here, definitely not parallel. A little better, a little better. Looks kind of parallel there. That, I think, is parallel at 0.5. T equals 0.5. The purple guideline appears to be parallel with the blue secant line. Okay. So yeah, it does appear that at some point during that first 1 second journey that the hammer took, there is a period of time where it was traveling exactly 4.9 meters per second, 0.5 seconds after being released. All right, let's go ahead and actually move on to what we want to do now, which is example 1's question, the question posed in example 1. So how do we estimate the instantaneous rate of change? So what the actual instantaneous velocity is at 0.8 seconds. I'm going to go ahead and turn off this exploring, so we don't need to look at that purple thing. We're just going to look on this side now. So how do we do that? Well, the way we can do this is by creating an interval. So we'll start the interval at 0.8, at t equals 0.8 on the graph, and then let's make the interval, the time interval, really small. Let's just do 1/10 away, so 0.8 to 0.9. And I've added the slider here for h where we can make the interval smaller. Like we could make it point, from 0.8 to 0.87 instead of all the way to 0.9. Okay, we'll leave it at 0.1 in length for now, but yeah. Okay. All right, so in order to find the average rate of change on this interval, we do what we did earlier, right over here. Final minus initial divided by final minus initial. Rise over run. So if we do rise over run for this, we're going to go ahead and get, let's see, we're going to do the value, the y value here. So 3.969 minus 3.136, that's what these two values are, divided by 0.9 minus 0.8. If you do that, you get 8.33. So this gives us an estimate for the instantaneous rate of change. It's only an estimate, and it's not as accurate as we'd like. We can make it more accurate by shrinking the length of the time interval. We can do this by modifying this h slider. So let's go ahead and modify it, and we can watch this number right here change. It's decreasing. It's getting smaller. And it seems to be approaching 7.8449. And if we take it all the way down to 0, we get undefined. Now, why do we get undefined if we bring those 2 points together? Well, one way to think about it is just purely from a geometric point of view. Normally what we're doing here is we're trying to find the slope of a line connecting these 2 points. Well, if h is 0, h is the separation. If there's no separation, then the 2 points overlap. And is there a unique line that goes through one point? No. There's an infinite number of lines that go through this point. In a sense, you can think of it as a whole circle's worth of lines, if that makes sense to you. There's a whole circle's worth. So we can't actually do that. So I have this as close as the slider will let me based on the settings I have here of a time step of 0.0111 thousandth. And we get an estimate of 7.8449. Okay. The other reason why we get undefined if we take it a step further is because, look at the bottom here. We're doing 0.8 minus 0.8. We're literally dividing by 0. So that's not good. Let's bump this back up. Okay, so 7.8449. And if we really wanted to, I think we could even make this, let's see here. Let's see, I was going to push Desmos until... Here we go. With a lot of zeros here, what do we have? 7.8400002. So it really looks like the trend here is if we kept going and making this smaller and smaller and smaller, it seems like it's approaching 7.84. Okay. So the actual, if you actually use calculus, the actual instantaneous rate of change is 7.84 exactly. So the whole idea here, hopefully that this is communicating, is that if you shrink your interval and make the step size small as possible, you will get a good estimate. So now I did this with the interval beginning at this point, and then the right endpoint, how far away we travel to the right, is getting smaller. We could have done this from the other way, where we actually allow this point to, let's say, go to the other side. We could have had starting from a tenth away to the left and then shrinking downward. And we get the same sort of idea. Just only at that point we get undefined. Okay. And if we look at my example 1 and how I calculated it by hand, we did end up getting 7.84 as well, using our calculations and doing some rounding here. But this is a visualization for what's going on, and yeah, hopefully this was helpful.